So I wanted to say thank you for the opportunity to speak. It's very good to be back in Utrecht, even if it's only in this sense. I will talk about singular chains on Lie groups and the Cartan relations. And I should say that this is joint work that I've done with Alexander Quintero, who was also a student at Utrecht. So this is somehow appropriate. All right, so let me tell you what this talk is about. So here's the plan for the talk. It's divided in 3 parts. The first part will be about singular chains on Lie groups and their Cartan relations. The second part will be about what the first part has to do with Chern-Bay theory and sort of a stronger version of the results I'll tell you in the first part, which holds in the case of compact Lie groups. And the third part will be more about classifying spaces of compact Lie groups and local systems on them. That's how it's divided. Let me, I should also say that I was informed that there was time for questions and that the organizers are flexible with respect to time. So if someone has a question or a comment or a correction, please make them. There's also a chat if someone prefers to make the questions on the chat. All right, so let me tell you what this is about. So I will fix a simply connected Lie group G with Lie algebra frag G. And for the first part of the talk, it will not be important that G is compact. Later, we will assume that it is compact, but at the beginning, it doesn't matter. Okay, so we will denote by C of G the space of smooth singular chains on G. So this simply means the graded vector space generated by smooth maps from simplices to G. This is the space you use to compute singular homology of any manifold. And
with real coefficients?
With real coefficients, yes, that's right. This space has the algebraic structure of a differential graded Hopf algebra. So let me remind you what a Hopf algebra means. It means that you have two pieces of structure. You have a product, and you also have a co-product in this vector space. And this product and co-product, they're not independent, but they're related. They're related by this identity. That's what a Hopf algebra means. It means that you have an algebra, which is also a co-algebra, and two are compatible in this sense. All right, so the point is that singular chains on a space, in general, it's a co-algebra. But if the space is additionally a group, then that gives you also a multiplication, and the multiplication and the co-multiplication, they interact well, and they make the space a Hopf algebra. So let me remind you how this is constructed. How is the product constructed? I mean, the co-product is present for all spaces. So I won't remind you about that. So I'll remind you how the product is constructed. So you need a multiplication map move from singular chains, tensor singular chains to singular chains. And this multiplication map is constructed as a composition of two maps. You first apply what's called the Eilenberg-Silber map that goes from the tensor product of chains with itself to chains on the product. And then you use the mapping used by the multiplication on the group to go to singular chains on the group. So the compositions of these two maps is what gives you a product in the space of singular chains. Now, as you see, well, it's only in the second part that you use the group structure. The first part is something combinatorial that does not depend on G being a group. It's something that would be present for any space. And it's given by a formula that it's something purely, well, combinatorial or topological. You can write it in this way. As a sum given two simplices on two singular chains on a space, you can produce a singular chain on the product space in this way. The formula, I mean, it's not very important that you have it in your mind at this moment. What is important is that it is simply a combinatorial formula, which is dependent on the fact that even though the product of two simplices is not a simplex, it is true that the product of two simplices lives inside a cube, and a cube can be divided into simplices, because in a cube of dimension n, you have n factorial simplices. So it's not very important. If you don't remember the formulas, it's not very important at this moment. It's just the fact that you have a well-defined product in this space, and this well-defined product is given by a composition of two maps. One of them is universal, topological, in terms of, well, ways of dividing a cube into simplices, and the other part uses the multiplication rule. So that's this differential graded Hopf algebra of singular change on a group that I will consider for the talk. Okay, so now let me.
Camilo?
Yes?
Could you remind what the coproduct is, if possible?
The coproduct is also is something that is induced by the diagonal map. So if you have any space, you have a diagonal map from the space to two copies of itself, which embeds the space into the diagonal. And just similarly as you did with the product, you can combine that map with a combinatorial map to give you, this combinatorial map in this case is called the Alexander Whitney map. So if you compose the diagonal map with the Alexander Whitney map, you get a coproduct on the space, and this coproduct gives it the structure of a co-algebra.
Is the Alexander Whitney map inverse to the Ellenberg?
It's up to homotopy. It's not strictly inverse, but it's homotopical inverse.
Okay, thanks.
Mm-hmm. Okay, so the group ring and singular chain. So, well, the algebra of singular chains on the group has a subalgebra, which is those chains of degree 0. And these chains of degree 0, well, they're just a vector space generated by the 0 simplices, which are the elements of the group. So that's simply the group ring of G. So I want to think of this algebra of singular chains as some sort of extension of the group ring of G. And now the point is that, so if you look at singular chains in degree 0, you get a group ring. And for the group ring, if you want to consider representations of the group ring or modules over the group ring, that's the same thing as representations of the group. And representations of the group is something that you can describe infinitesimally in terms of representations of the Lie algebra, right? That's the whole point of Lie theory, that you can compare infinitesimal and global information. And so this subalgebra of the algebra of singular chains, which is the group ring, is something whose modules can be described infinitesimally. So the question that I want to address in this talk is, how do you, at least in the first part of the talk, is how do you describe infinitesimally the modules, not over the group ring, which is the part of degree 0 of the algebra of singular chains, but the modules over the whole algebra of singular chains. So just as you can describe representations of the group, which are modules over the group ring in terms of the Lie algebra, I want to look for a way of describing modules over this algebra of singular chains in terms of the Lie algebra. That's the question, the first question I want to address. Okay, so the answer is given by the Cartan relations. So probably most of you know what I'm talking about here. These arise as follows. If you have any Lie algebra, it may or may not be finite dimensional, you can produce another differential graded Lie algebra associated to G as follows. As a graded vector space, Tg is going to be two copies of G, one in degree 0 and one in degree -1. And this vector space has a bracket which is given by these formulas, and these relations are known as the Cartan relations, right? And they arise, as most of you will recognize, from the identities that are satisfied by contractions and Lie derivatives when you have a group acting on a manifold. So the algebra of vector fields and differential forms, they act on differential forms but by Lie derivatives, but they also act by contractions. And the contractions and the Lie derivatives are related by these Cartan relations. So this Lie algebra Tg is simply the universal algebra that encodes the Cartan relations, in the sense that having an action of Tg is the same thing as having an action on a space by contractions and Lie derivatives, satisfying whatever identities are satisfied by contractions on the derivatives on a manifold. So here's
Camilo,
yes.
Is this a Lie algebra of the tangent group of a Lie group? Is the same? Is it the same?
This is a differential graded Lie algebra, right?
Ah.
This is a differential graded Lie algebra, and yeah, it's not just a Lie algebra; it's graded, and that's important.
Okay.
All right. So this is what I said before. That suppose that G acts on a compact manifold, and this is sort of the the place where these relations come from, right? So if you have a group acting on a manifold, then the Lie algebra of the Lie group acts on differential forms, but more is true, right? You have the whole Lie algebra TG acting on differential forms because you have Lie derivatives, but you also have contractions. And the relations I wrote before are precisely the relations that are satisfied by the contractions and the derivatives. So this TG is universal for the Cartan relations. Right. So now the result that I want to mention is that there is an equivalence of categories. So the following is that there is an integration functor that I will denote by I for integration, that takes representations of this differential graded Lie algebra TG and produces modules over the algebra of singular chains in G. And this functor is an equivalence of categories. Here I should say that for this theorem to be strictly true, one needs to qualify it by restricting to a certain type of modules which are sufficiently smooth, right? So here there are some adjectives that I'm omitting, but this is fundamentally correct. If you assume representations to be sufficiently well behaved, then such a theorem is true. I should say that this theorem it is an extension of the usual correspondence between representations of the Lie algebra and representations of the Lie group because the category of representations of the Lie algebra embeds into the category of representations of TG. So this strictly extends the usual correspondence. This embedding is simply a left adjoint to a forgetful functor. So this is contains sort of, via this inclusion, it contains the usual correspondence. This is a theorem that you can prove very explicitly, and I can tell you exactly how the proof is done because it's very easy. So let me tell you how you prove this theorem. So what it is that you need to do, you need to start with the representation of this algebra, of this differential graded Lie algebra TG. So you have a representation of this on some complex of vector spaces, and out of this data you should be able to produce a module over the algebra of singular chains on the Lie group G. And you can do it completely explicitly. So let me tell you how this is done. So you start with this representation row, and out of this representation row you can construct an equivariant differential form on the Lie group. So this is going to be a non-homogeneous differential form. So it has 0 part and 1 part, arbitrarily high degree. So it's a sequence of differential forms on the Lie group, and they take values in endomorphisms of V. V is the space on which the Lie algebra is represented. And how are these differential forms constructed? Well, these differential forms, if I require that they are equivariant, then they will be determined uniquely by the value they take at the identity, right? Because the group acts transitively on itself. So by requiring that if I want the form to be equivariant, I only need to say what its values are at the identity. And the values it takes at the, yes?
Just to make sure, equivariant under what action on the group? Left, right, both?
Left action. I guess you could pick your convention at some point, but I think the convention I chose is left action.
Okay.
Yes.
Also, quick question. When you talk about representations, does it include the differential?
Yes, it does. Yes, it does. So yeah, that's a good point. So if I when I write this rho, what I mean is that B is a chain complex, and the morphisms of B is seen then as a differential graded algebra.
Mm-hmm.
Then a differential graded Lie algebra, and rho is a morphism of differential graded Lie algebras.
Thanks.
That's what I mean. Yes. All right. So you have this differential form. So you specify it at the identity by this rule. So what you do is you do what the representation rho does on the contraction, and you do it k times. That specifies the value at the identity, and then you move it by equivariance to any other point in the group. And that gives you a differential form in the Lie group for each k. Now, this formula doesn't look very skew symmetric, right? Because you're just choosing an order, but precisely the fact that you have the Cartan relations tells you that these contractions commute, and therefore it is skew symmetric, and it does define a differential form for you. Okay. So I'm saying for now that given a representation of TE, you produce a differential form on G. And this differential form that I just defined, it turns out to satisfy some equations. And the equations it satisfies are these three equations. It satisfies, the first equation says that the derivative of the zero part recovers the action by Lie derivatives. The second equation tells you that it behaves well with respect to multiplication. So it's some sort of multiplicativity condition, but it's different from the multiplicativity condition that arises, for instance, in Poisson geometry, where you would change this wedge product by a sum. This is a different kind of multiplicativity condition. It tells you that when you pull it back by the multiplication map, you get a product of these two forms, and this makes sense because these forms are not homogeneous, right? So you mix all degrees and it makes sense. And the third equation says that the two differentials, as Eckhart mentioned, there are two differentials now. There's a differential that comes from the RAM, and there's a differential that comes from B, and these two differentials are related. So these equations will be satisfied by the form alpha as long as you started with a representation of TG. And now there is a different way in which you can encode these equations. So the equations that I wrote here, perhaps they're not, it's not very clear what they mean, but there's a different way of writing them down. You can use what's called the Bott-Schulman Stashev complex of the Lie group G, and recall what this is. This is a model for the cohomology of the classifying space of G. So the way it is constructed is that you consider differential forms and arbitrary copies of G, and this space of differential forms and arbitrary copies of G has two differentials, one which is the RAM and one which is simplicial. That depends on the simplicial structure induced by the group multiplication. And this forms a double complex, and indeed it forms a differential graded Lie algebra. Sorry, a differential graded algebra. And so in terms of this differential graded algebra, you can interpret the equations that I told you that alpha satisfies. So you see, alpha is a differential form on G, so you can view it as living in this first column of the Bott-Schulman complex. You can think that alpha, which is a differential form on G with values in endomorphisms, you can think that it lives in this first column on the Bott-Schulman complex. And you view it, and if you view it as a living there, then the equations that I mentioned before are equivalent to saying that alpha satisfies the model Cartan equation. So this alpha that you produced out of rho is a model Cartan element in this Bott-Schulman complex. So this suggests that one may think of this as some sort of flat connection on the classifying space of G, and indeed I think this is the right interpretation, because the differential form you produce is exactly it's something that behaves like a flat connection on BG. Okay, so now I told you the intermediate steps, which was to produce this differential form alpha, and then how do you go from alpha to constructing a module over the algebra of singular chains? Here's how you do it. I need to give you a module over the algebra of singular chains. So I need to tell you a map from the algebra of singular chains to the algebra of endomorphisms of B. This should be a map of differential graded algebras. That's what a module over singular chains is. So I need to produce for you this map I of rho, which is a map of differential graded algebras from singular chains on G to endomorphisms of V. And this is simply done by integration. You just use the Ram's map. You take a differential form and you integrate it. Because you integrated it, this is a form with values in endomorphisms of V. When you integrate it, you get a matrix. And that's the action. And it turns out that all these conditions that I wrote for the form alpha are precisely the conditions that you need so that this map is an algebra map. So this homomorphism is a map of differential graded Lie algebras. And that's a proof. It's very explicit. So a summary of the situation is this. You start with a representation of TG. Out of this representation of TG, you produce a matter Cartan element in the Bott-Schulman complex explicitly by just saying what it is on the identities and moving it by equivariance. And then you take this form in the Bott-Schulman complex and you integrate it. And this condition that it is a matter Cartan element is precisely what you need so that integration will give you an algebra map. And that's how you produce a module. And then you check that if you make the right, if you put the right conditions on the modules, then, and the right conditions is that the modules are local in sort of the obvious sense. If the modules are sufficiently local, then all these arrows are bijections and you get an equivalence of categories. Right, so that's the first result. This ends the first part of the talk. All right, so this is something, yes?
Camilo, I have a short question. So you say it works for good enough modules?
Yes.
So what's a canonical or good example of a good enough module?
Right. So I want this to be something like, well, in proving this theorem, you can, the way I did it is actually you can construct a functor in the other direction. And the other direction, well, if this is an integration, the other functor is a differentiation. So what you need is, well, for the module to be enable for you to apply this differentiation functor, you need to be able to take, well, derivatives with respect to the parameters. So you need that the action, so the module structure, so the action of chains on the space varies smoothly with respect to the parameters. And that's what I mean.
Yeah, but let me make my question more explicit. What are the modules that you're actually using in practice? What are the useful modules that we should think about?
All right. So so you're asking me for examples, or?
Yeah, or whatever. What kind of examples should we think about when thinking?
Yeah. Okay. One example is the Chevalier-Eilenberg complex of a Lie algebra. So if you have a Lie algebra, you take the Chevalier-Eilenberg complex, and then the Lie derivatives act by the coadjoint action, and the contractions act by contraction, and that's an example. And the Bay algebra is another example. And in general, as I mentioned before, whenever you have a representation of a Lie algebra, a finite dimensional representation of a Lie algebra, you can produce an example of a representation of TG. So you have at least as many examples as you have for representations of G. So any finite dimensional representation of the Lie algebra will give you an example of this.
And for those two examples, what are the integrations for the wedge G star and for the wedge algebra?
Right. So for the Lie algebra, so let's see, for the Chevalier-Eilenberg complex, you see the integration procedure tells you that, I mean, it doesn't change the vector space. So if you fix a vector space, just like in Lie theory, it tells you that the vector space stays the same, but now you have an action of the whole group. And here it tells you that in the Chevalier-Eilenberg complex, you have an action of the singular chains on G. So what I'm saying is that in the Chevalier-Eilenberg complex of a Lie algebra, there is an action of the space of singular chains on G, which is integrating this infinitesimal action. Mm-hmm. And now this algebra of singular chain of Chevalier-Eilenberg complex, of course, lives inside differential forms on the group, right? And this corresponds to the fact that singular chains on the group acts on, well, the group acts on itself by conjugation, right? And then this is somehow a restriction of the fact that an infinite dimensional version of this result would be that singular chains on the group act on singular chains, sorry, on differential forms on the group And the module that you obtain by integrating the Chevalier-Hilbert complex is a submodule of that. So it corresponds to the action by conjugation of G on itself.
Okay, thank you.
Camilo,
Yes.
continuing with examples of presentations, let me ask you the following. First, if I see the Lie algebra as I don't know, a Lie algebra with a single point, and then I look at the tangent VB algebroid, isn't it the same essentially of this TG?
Sorry, can you repeat the question? I'm not sure I understood.
Yeah, that you take for each Lie algebroid or each Lie groupoid, you can take the tangent prolongation, and this is called the VB vector bundle groupoid or vector bundle algebra. And I was wondering whether if this TG is essentially the same as the tangent of the Lie algebra. And
it sounds like it's probably true. The truth is I don't know this language well, so I cannot tell you. But it sounds like something like that is probably true. I don't know the answer.
Then I see. But then, sorry.
I would expect it's more like the odd tangent bundle, right? Because it's a
right. I mean, it is important that it's graded, right? That's for sure. So I mean, this is something about, well, the grading is important.
Yeah.
Not just a Lie algebra; it's a graded Lie algebra.
And this approach suggests to see also or to ask this question that I want to do, that whether if representations up to homotopy somehow can be framed into representations of this object, if there is any relation between representations up to homotopy and representations of TG.
Well, there is I will say something about that later. So what this should be, well, that's where I want to go later. But so okay. I think the way to think about this, as I mentioned before, is they should be thought of as flat connections or flat graded connections on the classifying space. And then if you think of them that way, then then you can also think of them as being some sort of representations of the infinity groupoid of the classifying space. But I will say something about that in a moment. Yeah, that's one of the points I want to make later.
Could you comment about the degrees of this equivariant form? Why it sits in?
Yeah, exactly. That's very good. So the degrees are so that I said that this was a motor Cartan element. So the degrees are so that this is degree 1.
But it's not degree 1 in the total, only in this one direction.
So you see, if you see them inside the Watt-Schulman complex, let's see. Right, so you want this thing to be degree, is a differential form with values in matrices, and you want this to be degree 1, right? So because this is already shifted by 1, then you want that the form degree is equal to the negative of the matrix degree. That's what you need so that the total degree is 1 in the Watt-Schulman complex. That's right. Is that, which is that right? Which is consistent with the definition we made, because, sorry, let me show you. Right, remember the definition we made was this. Right, the definition was that the differential form alpha, when you evaluate it in k vectors, you need to use the contraction k times. So you reduce the degree by 1 k times, so it has degree minus k. So it's a k form of degree minus k, but because it lives in the first column of the Watt-Schulman complex, and it has total degree 1, which is what you need if you want it to be motor Cartan.
So doesn't that suggest that there should also be kind of an enlargement where you have kind of forms on the different parts of the Watt-Schulman, like on the different products of?
Yeah, that's right. That's a very good point. One can consider more general modules, and presumably it corresponds to the fact when you, right. So that will give you, instead of giving you strict representations of the algebra of singular chains, that would correspond to A infinity representations of the algebra of singular chains. Okay. So that's something that we can also consider, and indeed, and the sort of the construction that we use in the proof can be adapted to that situation as well, because everything is compatible with multiplication at all levels. So that's true. So that suggests that one can consider more general motor Cartan elements, and they will correspond to not to just strict modules over the algebra of singular chains, but to infinity modules over this algebra. I think that's right.
Oh, okay, thanks.
Are you Francis? You're Francis, right?
Yeah.
Yes. Okay. Hey, Francis.
Hi.
Okay. All right. So this is what I wanted to say about Lie groups. Now, the next part of the talk, I want to specialize the situation to the compact case, because what happens is that in a compact case, you can make a stronger, you can prove stronger results, and also the relationship with the chain Bay theory appears. So let me just very briefly remind you what chain Bay theory is about and how it's related to the story I just told you. So chain Bay theory is a geometric theory of characteristic classes. So it's a way to describe characteristic classes in terms of geometry and Lie theory. And very briefly, this is how it's constructed. You start with a principal G bundle over space X. And the point is that principal G bundles are classified by maps to the classifying space. And this map is well defined up to homotopy. And therefore, there is a well-defined map at the level of cohomology from the cohomology of BG to the cohomology of X. And what Chern and Bay did, one of the things they did is to describe this map intrinsically in terms of the geometry of the principal bundle. So the way they did it is, there's several versions, but one way of constructing it is you construct what's called the Bay algebra of the Lie algebra, which is, well, in the language that I'm using here, is the Chevalley-Eilenberg complex of the Lie algebra TG. And this algebra behaves as differential forms on EG. So it's an algebraic model for differential forms on EG. And its basic part behaves as the cohomology of BG, and it can be computed to be equal to the invariant polynomials on the Lie algebra. And this Bay algebra has the property that a connection on P is the same thing as a map from the Bay algebra to differential forms on P. It's exactly the same information. Having a connection of P is having such a map. And so that once you fix a connection, you get such a map, and by restricting to the basic part, you get a map from the invariant polynomials of the Lie algebra to the cohomology of X. And this map is a geometric way of describing the map from the cohomology of BG to the cohomology of X. That is what chain Bay theory is. Now I want to tell you what this chain Bay theory has to do with the story I just told you about singular chains in G. That's the next thing I want to discuss. So the following happens. The theorem I told you before is it's an equivalence of two categories of representations. I said that the category of representations of TG is the same thing as the category of modules over the algebra of singular chains on G. Now, it turns out that when G is not only simply connected, but also compact, you can make a stronger claim. You can promote the theorem I told you about to an equivalence of differential graded categories, not only of categories, but differential graded categories, which is a strictly stronger result. So for this, you need to add some extra structure to this category of representation. So you started with this category of representations of TG, and you're going to promote it to a category of representations of TG, which I will denote with a bar. And that means having a DG category means that if you fix two objects, then the space of morphisms between them is not just a set, it is a chain complex. So home spaces are chain complexes. That's what a DG category is. For instance, a DG category with one object is a DG algebra, right? Now, the home spaces in this DG category are equivariant cohomology groups. And that's how the chain Bay theory enters. So you can promote this category, which is just an ordinary category, to a DG category by having the home spaces be equivariant cohomology groups. And you can do the same thing for the category of modules over singular chains on G. So you can promote it to a category of what I'm calling mod bar, which are modules, but now seen as a differential graded category. And the home spaces, while in the previous case were given by equivariant cohomology spaces. Here they're given by Hochschild cohomology spaces. So this category of modules over singular chains on G can be promoted to a DG category by having the home spaces be Hochschild cohomology spaces. Now, the theorem I want to mention that we proved with Alexander Quintero is the following. It says that if G is simply connected and compact D group with the algebraic G, then there is an A infinity equivalence of differential graded categories. So this category rep of TG is A infinity equivalent to a category mod of C of G. So this is strictly stronger than the theorem, the first theorem I mentioned, because now it takes into account the cohomological information of the categories. So you put more information into the categories, you make it into a DG category, it contains more information. And the theorem is that in the compact case, you still have an equivalence. But it will be an A infinity equivalence of differential graded categories. So what I want to do next, the proof of this theorem is not quite as easy as the previous one. So I cannot give it in all detail, but I can tell you what the steps are in the proof and what the ingredients are for the proof. So that's what I want to do next. So let me tell you what are the ingredients that you need for this proof. The first ingredient is Chen's iterated integrals, which is a way to construct differential forms on mapping spaces. And the way in which it enters in this construction is via a version of the Ram's theorem that I will discuss. Second ingredient that enters is an A infinity version of the Ram's theorem. I will say something about this in a moment. But the idea is that the usual de Rham theorem can be corrected to a much, in my opinion, more natural and more satisfying result, which was done by Guggenheim in the 70s or 60s even maybe. The other ingredient that enters is a non-commutative Bay algebra of Alexeyev and Meinrenken, or at least one of them, because they constructed several ones. And the way in which this appears is the following: is that you see this Bay algebra in Chen Bay theory, it's a commutative algebra, and it's used for defining maps to differential forms on principal bundles, which are commutative algebras. But the algebras that appear here when you're doing these constructions, they're non-commutative. For instance, the Bott-Schulman complex is a non-commutative algebra. So in order to construct versions of the Chern-Bay map in that algebra, you need a non-commutative version. And that's one of the applications that they use this non-commutative algebra for. And the other key ingredient in the proof is this Vanessa map that many of you probably know about. So let me tell you how these ingredients fit into the story. So the map for the proof is as follows. You need to find A infinity equivalence of DG categories, and what you do is you can connect them by a zigzag of equivalences. You cannot go from one to the other directly, but you can find a zigzag of equivalences that connects one to the other. And these intermediate categories that I'm writing, BSSG and BSSGG, they're sort of intermediate categories that one can use to compare them, and BSS stands for Bott-Schulman-Stashev. So the way of going from this infinitesimal thing to these modules over singular chains on G passes through an intermediate step, which is related to these Bott-Schulman-Stashev algebras. And this one is a smaller version of this, which is invariant. I will say something about it in a moment. For the moment, this is only meant to give you sort of a scheme for what's the structure of the proof. In order to prove that the first one and the last one are equivalent, you just need to write these 1, 2, 3 equivalences with respect to these intermediate categories. All right, so let me tell you a little bit more about how these ingredients that I told you enter into the proof appear. So Chen's iterated integrals, they are a way to construct differential forms of mapping spaces. So let me tell you how they are defined, and there are different versions of them depending on the purpose that you want to use them for. But one of the simplest possible versions is as follows. The thing that they will produce for you are differential forms of mapping spaces. So the simplest possible mapping space that you can consider is the path space of a manifold. So let's see how Chen's iterated integrals can be used to produce differential forms on the path space of a manifold. And this is done as follows. I'll show you how to produce differential forms on the path space of M given tensor products of differential forms on M. So what you do is you define Chen's map by this composition. You start with powers of differential forms on M. That lives naturally inside differential forms of K copies of M, just by pulling back by the projections. Then you can use the evaluation, the natural evaluation map, to pull back the differential form to the simplex times the path space, and then you integrate over the simplex. And if you follow this composition, you start with K differential forms on M, and then what you end up with is a differential form in the path space of M. Now, the reason that's called iterated integrals is because of this last step here. When you write this down explicitly, you integrate it over the simplex, and then what you get is an integral over T1, and then over T2, and then over T3, and that's the reason why this is called an iterated integral. But this can be written very canonically in this way, and that's a way to produce differential forms on mapping spaces.
So what is the natural evaluation?
Sorry?
What is the natural evaluation?
Right, so the natural evaluation map, yeah, I should have, let me write. So the natural evaluation map, this F, it goes from, oh, sorry, I should have written differential forms here. I'm sorry, I missed, there should be omega here and omega here. So this evaluation map is a map that goes from the simplex times the path space of M to the power K. So what you do is you take K times and a path, and well, and then you evaluate the path at those times. It's completely tautological, right? So if you have a point in the simplex and an element of the path space, by evaluating the path at these K times, you get K elements of M. That's this tautological evaluation map. And then by pulling back along this map, you get a differential form in the simplex times the path space. And then you integrate over the simplex and you get a differential form in the path space of M.
Thanks.
Here you view the simplex as like an interval where you've picked K points in time or something?
Exactly. So yeah, that's exactly the right interpretation. In particular, there's nothing special about the path space. You could take any mapping space and replace the simplex by a configuration space of points in the space that you're starting with. So this is something that would work for any mapping space, right? It's something completely tautological. So here the space, as Francis said, I think it was Francis, should be thought of as the configuration space of points in an interval. That's right. So this is completely tautological. Now the point is that this way of producing differential forms on mapping spaces, because it's very tautological, it has very interesting properties. In particular, it can be used from the point of view of the story I'm telling you. It can be used to produce an A infinity version of the Ram's map. So let me tell you how this goes. So there is a theorem which is due to Guggenheim in the 60s, which says that the Ram map, let me write it down explicitly. So what's the usual the Ram map? You start with a differential form omega. So the usual the Ram map, what it does is you take a differential form, and out of this you produce a singular cochain on a manifold. And the way you do it is you take omega and you view it as a cochain by, well, you evaluate it on a chain, right? So how do you evaluate it on a chain? You take the chain, you pull back omega, and you integrate over the simplex, right? That's the Rams map. And this map, what one learns is that this map is a quasi-isomorphism of chain complexes. And in fact, it induces an isomorphism of rings at the level of cohomology. However, this map is not an algebra map. And it shouldn't be an algebra map because the thing on the left is commutative and the thing on the right is non-commutative. So you wouldn't expect to have an algebra map there. And so it is surprising that even though you have a map which is not an algebra map, at the level of cohomology, it does become an algebra map. That seems like a very unnatural statement. And what Guggenheim observed is that the reason why this is true is because this, the Ram map, is just the first part of an A infinity map, which he constructed. And this A infinity map, the higher order parts of this A infinity map, they are given in terms of iterated integrals. So you can use the formula that I told you about Chen's iterated integrals to produce the higher order correction terms to the Ram map so that it becomes an A infinity map. So this is what I'm calling the A infinity version of the Ram's theorem proved by Guggenheim, which explains why even though you don't have an algebra map at the level of chains, you do have an algebra isomorphism at the level of cohomology. Yeah, this is the way in which tangent integrals enter in the story I'm telling you. Now, why is that relevant for the discussion of the theorem I'm explaining? It's the following reason. Right? Remember the Bott-Schulman-Stashev algebra. It's this algebra which is made of differential forms in arbitrary copies of G. As we mentioned before, this is a differential graded algebra. It is non-commutative, and it is a model for the cohomology of the classifying space of G. So this means that once you, and it's sort of implicit in the notation, this behaves as this is something that one can think of as being a model for differential forms on the classifying space of G. Right. Now, what one needs to do in the proof of the theorem is to find a version of this A infinity, the Ram theorem, but not for a finite dimensional manifold, but for a classifying space like this. So one of the key steps in the proof is to find the following theorem. Is that there is a version of Guggenheim's A infinity quasi-isomorphism for classifying spaces. So it means that using essentially the same formulas that Guggenheim used in terms of Chen's iterated integrals, you can produce an A infinity quasi-isomorphism between two different models for the cohomology of the classifying space of G. And these two different models are the Bott-Schulman-Stashev algebra and this thing on the right. This thing on the right is the algebra of is the algebra of Hochschild cochains over the algebra of singular chains on G. So what happens here is that very much in analogy with Guggenheim's theorem, where you constructed an explicit A infinity quasi-isomorphism between two models for the cohomology of a manifold. This uses the same formulas to provide an A infinity equivalence between two models for the cohomology of the classifying space of G. And these two models are the Bott-Schulman algebra and this, which is Hochschild cochains on the algebra of singular chains on G. Now, this enters into the proof of the theorem because, as I told you before, the home spaces in the category of modules over singular chains on G, these home spaces are Hochschild complexes for this algebra of singular chains. So in order to compare these two categories, you need an explicit way of going from this Bott-Schulman category to Hochschild complexes over the algebra of singular chains on G. And the way in which you can compare them is using this A infinity map. Now, as was suggested by as was suggested by Francis before, right? In the construction I mentioned, we only considered very special kinds of motor-Cartan elements in the Bott-Schulman complex, those that came from strict representations of the Lie algebra TG. But in principle, if you have any kind of motor-Cartan element in the Bott-Schulman complex, you can push it forward along this quasi-isomorphism. And then you'll get a motor-Cartan element in the algebra Hochschild cochains over the algebra of singular chains. And these are precisely, well, in correspondence with A infinity modules over the algebra of singular chains. So indeed, if you wanted to sort of consider a more general situation where you also deal with not only with strict modules, but with A infinity modules, you can do it because this map is an A infinity map and plays well with respect to multiplication. But because we were interested in the situation that came from the representations of the Lie algebra, then for now we restrict to this. Okay, so this is how Guggenheim's theorem enters in the proof. Now the other sort of construction that enters in the proof is the non-commutative Bay algebra, and the reason is the following: as I mentioned before, this algebra is non-commutative. So if you want to construct a Chen-Bay map taking values there, you need a, well, the commutative algebra doesn't work. It's universal with respect to commutative algebras, not with respect to non-commutative ones. So you need a non-commutative version of the Chen-Bay construction, and that was done by Alex F. and Mein Renken, and they used it to, well, for several applications in Lie theory, but one of the applications they used it for is to construct precisely characteristic classes in this Bott-Schulman complex. I will tell you in a moment how their construction enters, but first I have to tell you about the other ingredient, which is the Vanessa map. And the Vanessa map is a way of comparing Lie group cohomology with Lie algebra cohomology. And this was originally constructed by Titus Van Est. And there has been a lot of work by other people, Weinstein and Xu, Kreinig, and there's many others, some of you, some of which are here in this talk. But sort of, well, yeah, it started with Van Est, and as far as I know, it was Weinstein and Xu who extended it, and Kreinig extended it even more, and then there's been subsequent works. But for the purposes of this discussion, there are all sorts of versions of the Vanessa map. There's versions for groups, there's versions for groupoids, there's versions that take values in singular, on group cochains, but with values in the Bott-Schulman algebra. I mean, there's all sorts of variations on this idea, but the version that I will use for this purpose is a version that I think was proposed by Marius and me at some point, and also by Rajan Mehta in some other description. But it's a version that takes, I mean, not only does it go from group cochains to Lie algebra cochains, but it actually leads to a map that goes from the Bott-Schulman complex to the Bay algebra of a Lie algebra. So this is a version that enters the discussion. So the Vanessa, one of the versions of the Vanessa map takes the Bott-Schulman complex and maps it to the Bay algebra. Now, what does this mean geometrically, right? The Bott-Schulman complex is a model for the cohomology of BG, and the Bay algebra is a model for the cohomology of EG. So this Vanessa map modules simply the pullback by the projection from EG to BG. So it's not in itself, it doesn't contain a lot of information. It's just the map from, well, the pullback map from EG to BG. Now, what we prove in this, in improving the theorem is the following. When you have the Bott-Schulman complex and you suppose that G is a compact Lie group, then you can find a sub-algebra of the Bott-Schulman complex that we denoted by the invariant part of the Bott-Schulman complex. And well, I won't go into details, but I mean, Bott-Schulman complex is forms on copies of G. So of course you have all sorts of actions on copies of G on that. and you take invariance with respect to one of those actions. Now, if the Lie group is compact, then this inclusion of the invariance into the whole Bot-Schumann complex is a quasi-isomorphism, right? Because taking invariance with respect to a compact Lie group doesn't change the homotopy class of the complex. So in the compact case, you can find a smaller version of the Bot-Schumann complex, which is the invariant part of the Bot-Schumann complex. And now the point is that when you restrict the Vanessa map to this invariant part, now it doesn't land in the whole Bay algebra, it actually lands in the invariant polynomials in the Lie algebra. So by restricting the Vanessa map to this Bot-Schumann, the invariant part of the Bot-Schumann complex, you land not in the whole Bay algebra, but you land in the invariant polynomials of the Lie algebra. So while this map on top is a model from the projection from EG to BG, this map at the bottom, it's a model from just the identity. It's just an isomorphism between two models for the cohomology of BG. And now, one way of proving that this is an isomorphism is because the inverse to this map is the map produced by Alexei van Maenrenken. So the inverse of this restriction of the Vanessa map to this invariant part of the Bot-Schumann complex, the inverse map is the map that Alexei van Maenrenken constructed using the non-commutative Bay algebra. So from the point of view of the structure of the proof that I mentioned before, the way in which this enters is that
Is that the non-commutative Bay algebra that you wrote in this slide?
I'm sorry?
Is the Bay algebra in this slide the non-commutative one?
In this slide is the commutative one, but the way in which it enters is that this map uses the non-commutative one via a symmetrization map. So here it's being used in a very implicit way. So it doesn't appear in the slide, but it's being used because the construction uses it.
Is this the only part of the proof that uses the compactness of G?
Yeah, this is the only part of the proof that uses the compactness of G. Exactly. So in particular, the infinity quasi-isomorphism that I said, the version of Guggenheim's map, it doesn't use the compactness. This is the only step where you use it. And you use it in knowing that this inclusion is a quasi-isomorphism. I wouldn't know how to, if it's not compact, then I don't know what happens. But this is the key step where you use it because you want to make sure that when you include the invariant part in the whole algebra, you stay a quasi-isomorphism, and that's what it enters. Yes. So with respect to the structure of the proof, then so here I can tell you how this works. So then with respect to these intermediate categories, here's how it works. This part of the equivalence depends on this infinity version of the RAM theorem, right? So now I can tell you how they fit into the scheme. So here is the A infinity, the RAM, right? And here, this comparison is given by the Vanessa map. And this inclusion is where you use the compactness. Right. So for this arrow, you use Vanessa, and the fact that you have this isomorphism where you use the non-commutative Bay algebra. Here it's just the fact, here is the only step where the compactness, and here is where you use the chance, the Guggenheim construction of the Ram's map. Yeah. So that's sort of the structure of the proof. Okay, are there any questions at this point?
Do you know that the theorem is false for non-compact groups?
Yes, because it's I mean, because chain Bay theory doesn't work for non-compact groups, right? I mean, well, I mean, So if you don't have the invariant polynomials will not compute the cohomology of VG for arbitrary groups. So when you specialize this theorem to you have an equivalence of categories, right? Of DG categories. So these categories are tensor categories. So they have a unit object, which corresponds to, you have to have a trivial representation. And you compute the endomorphisms of these trivial representations, you should get the cohomology of VG. But it is only true when G is compact. I mean, on the right-hand side, you do get it. You get the cohomology of VG, but on the left-hand side, it will only be true if G is compact.
And Camilo, what are the issues in extending this result to groupoids?
Right. I haven't, well, yeah, there are several issues. So the first thing is that even though there is a good definition of the Bay algebra for groupoids, I don't think that there is a good definition for what it means to take invariant part of the Bay algebra. So there's not a purely infinitesimal model for the cohomology of VG. This is something I tried to do and failed when I was writing my thesis. This is something I couldn't do, and as far as I'm aware, it hasn't been done. So I don't think there is a good analog for that part. I mean, there are other parts of the proof that you can try to generalize. Another step which is not clear to me how to generalize is the fact that it's not clear what you need to replace singular chains on G with, right? Because when you have a Lie group, singular chains on G becomes, as I said, a differential graded Hopf algebra. But if you have a Lie groupoid, then it's not quite a Hopf algebra. It will become something more like a category enriched on chain complexes. I mean, you need to find a different formalism because on the nose it doesn't quite become a Hopf algebra because, well, the composition is not defined it's not defined everywhere, right? So I think there are some steps which one can try to generalize, but these are the two main points where it's not clear to me what the right analogs are.
About the non-compactness, I mean, for the Cartan model of equivariant cohomology, there's this work of Ezra Getzler. So
that's right.
Maybe some of those ideas could be used.
Yes, that's right. Yeah. So I think there is one place where one can, but that's not purely infinitesimal, right? That uses the group explicitly.
That's right.
The work of Getzler. So one can try to replace it by something, but it's not quite completely infinitesimal. That's something that's sort of intermediate, right? It arises as some sort of a group cohomology with values in symmetric powers of the Lie algebra, which is sort of intermediate between the Bay algebra and the Bott-Schulman complex. It's not, so it would be some, maybe one can factor the result by going through the model of Getzler and then going from there to, and actually I think that's something we thought about a bit. So I think one can factor this Vanessa map along the Getzler model and then get something intermediate. I think that's right. Yes. There's also a paper of Bott which proves a similar formula. Okay, so are there any more questions about this part?
Can it generalize to like quantum groups or something like that?
Generalize to quantum groups. I'm not sure what you mean by that. What kind of thing do you have in mind?
Well, I'm not exactly sure, but I just thought like replacing the chains, for example, by some non-commutative algebra.
I don't know. I mean, if it can be, I would be very interested in learning about it, but I don't know how to do anything like that. So, okay, so far, I told you about these two results. One is for arbitrary groups, you have an equivalence of categories. Then for compact Lie groups, you have an equivalence of differential graded categories. Now, the last part of the talk, what I want to do is I want to discuss sort of an interpretation of these results from the point of view of the theory of local systems on the classifying space of G. So there's sort of a theory of higher local systems on spaces. So it's in principle, it has nothing to do with B theory. It's something about topology. So let me tell you how it works. So, well, this is supposed to generalize the local systems for cohomology that one learns. So it's supposed to generalize flat connections on a vector bundle, or if you want, locally constant sheaves on a space. And it turns out that you can generalize this in different ways. So one way to generalize flat connections is you can do flat graded connections, which sometimes are called super connections or equivalent connections. That's one way to generalize local systems, by thinking of them as flat connections and then taking the graded version of them. Another way is that if you think of local systems as representations of the fundamental group, then you can forget about the restriction that you only look at the fundamental group and look at the whole infinity groupoid of the space. And then you can think of local systems as representations of the infinity groupoid of the space. And since Matthias asked, when I say representation here, I mean it's homotopical, so it's in the weak sense. So this is the way in which the representations that Matthias was asking about arise in this setting. And another version which arises sort of in algebraic topology is as follows. If you have a space, you can consider omega. Here, omega doesn't mean differential forms. I'm sorry for the confusion, but omega here means the based loop space on a space. So what's the idea? The idea is that if you have any topological space, the based loop space of that space, it wants to be a group, right? Because you can concatenate paths. So it's almost like a group, except it's not strictly associative, but almost. But that's a technicality, you can sort of fix it. And the idea is that another way of defining local systems on a space is by considering modules over the algebra of chains on the base loop space of X. So if you look at these three definitions of what a local system is, they are just the natural generalizations of three different ways of thinking about ordinary local systems on a space. The first is the generalization if you think of local systems as flat connections. The second one is the generalization if you think of local systems as representations of the fundamental group. And the third one is the generalization you get if you think of local systems as modules over the homology of the base loop space. And there's a theorem which is that all of these possible generalizations of the notion of local systems, they are equivalent. And what this means is that for each of these notions that I told you about, you can organize these notions into a differential graded category, and the resulting differential graded categories are equivalent. So let me just repeat. So you have three possible ways of defining what a higher local system is on a space. And the theorem is that all these three different ways are essentially equivalent, just as the ordinary ways in which you can think of local systems are all equivalent, which is sometimes known as the Riemann-Hilbert correspondence. Now, this theorem that I'm writing here in blue is the work of several people. There's a paper with Bloch and Smith on the Riemann-Hilbert correspondence. There's work by Julian Holstein, and there's some work I did with Florian Schetz. And if you put all these results together, you get the story working in the sense that all the possible notions that you could have of a local system, of a higher local system on a space, they coincide. So because all these possible versions of local systems coincide, I will abuse the notation and write log of X for any of these versions of the category of local systems on a space, which is not just a category, but it's a differential graded category. Now, the other version, the final theorem I want to mention is the following, is that if G is compact and simply connectedly grouped, then the categories that we discussed before, they actually can be interpreted as being the category of local systems on BG. So the category rep bar of TG, mod bar of singular chains on G, they're actually quasi-isomorphic or A infinity equivalent to the category of higher local systems on the classifying space of G. This is sort of interpretation, the topological interpretation of these categories of modules. They can be thought of as higher local systems on BG. And from this point of view, if you look at the theorems that I discussed before from this point of view, you can think of them as providing sort of a categorified version of the Chern-Bay computation, right? Because Chern-Bay computation is, well, you're computing the cohomology of BG with a trivial local system, right? And what this is doing is extending the computation for arbitrary higher local systems that you can consider on BG, and describing this category of arbitrary local systems on BG infinitesimally in terms of the Lie algebra. So that's why I think that this equivalence of categories here can be thought of as some version of the Chern-Bay construction. Okay, so that's the final result. The way in which this theorem is proved is the way things are usually proved in Chern-Bay theory. You write BG as a limit of manifolds, and then use this approximation to prove the equivalences that you need. So you write BG, and again here you use the fact that G is compact to make it live inside of UN, and then you can write down BG as a limit of manifolds and use this approximation to prove the result you want. That's how you prove it. Okay, so that's the final theorem I wanted to mention. I want to end with two examples, sort of to make, to illustrate how the equivalence of categories relates to the computations in equivariant cohomology. So the first is what happens in the simplest possible case, right? So when I'm saying that two categories are equivalent, so it means that the endomorphisms of the trivial object should be quasi-isomorphic. Well, the endomorphisms of the trivial object in this infinitesimal category are, by construction, the invariant polynomials in the Lie algebra, and the endomorphisms of the trivial object in this category are the Hochschild cohomology groups of the algebra of singular chains on G. So when you apply, so these apply to a trivial representation is the usual, is you obtain the two known models for the cohomology of BG. On the infinitesimal side, you get this computation, and on the global side, you get that the cohomology of BG is the Hochschild cohomology of the algebra of singular chains in G. That's what happens when you use the trivial module. A more interesting case is when you consider the loop space of BG. So when you have any space, there is a natural projection map from the loop space, and here the loop space means the free loop space. So it's the space of all maps from the circle to BG. And there is a tautological map from the loop space of BG to G, which is just given by evaluating at 1, where 1 is seen as a point in the circle. So for any space, there's a loop space vibration that goes from the loop space to the space itself. And this loop space vibration is not quite a locally trivial fiber bundle, but it's almost a locally trivial fiber bundle, because the fibers, they look like, well, they look like the base loop space, right? By definition, the fibers of this map are the base loop space for each copy. And this is not quite locally trivial, but it's almost locally trivial. And so it has a Gauss-Manin connection. And the construction under the correspondence that I told you, if you think that this has a local system, and this local system can be represented in terms of this infinitesimal category, rep of TG, then there should be a natural representation of TG which corresponds to the Gauss-Manin connection for this vibration. And in fact, the Chevalier-Eilenberg complex of the Lie algebra G is the representation of TG that corresponds to this Gauss-Manin connection. And if you believe this, then you should believe that it should also be true, sorry. If you believe that the local system that corresponds to this loop space vibration is the Chevalier-Eilenberg complex, then you should believe that the cohomology of the total space of the vibration, which is the loop space of Vg, is the same thing as the equivariant cohomology of G acting on itself by conjugation, because G acting on itself by conjugation, as discussed before, corresponds to the representation of Tg, which is the Chevalier-Eilenberg complex of G. So from the point of view of this equivalence of categories, the fact that the Gauss-Manin connection for this loop space vibration is the singular chain, is the Chevalier complex of the Lie algebra, corresponds to the fact that the cohomology of the loop space of Bg is the equivariant cohomology of G acting on itself by conjugation. And that's how you recover this fact, which is known fact, but it's something that you recover from the equivalence of categories. Right, so this is the kind of information that is encoded in the equivalence of categories. Now, I should say that this is as far as I know about this so far, there is an additional question, an additional structure that I would like to understand better, but I don't at the moment, which is the following. In this special case, the homology of the loop space of Bg, it has additional structure. It has the structure actually of a homological conformal field theory, and that's what's called the string topology of the classifying space of G. So just like there is string topology operations for manifolds, there's also a version of string topology for classifying spaces of compact D groups. And so this that means in particular that the cohomology of the loop space of Vg has an additional structure, which is a Vatalin-Vilkovitsky algebra. And I think the Vatalin-Vilkovitsky algebra structure corresponds to the fact that precisely when G is compact, this object in this category of representation is a Frobenius object. So actually, when G is compact, the Lie algebra is quadratic, and when the algebra is quadratic, this object in this category of representations, precisely in that case, when it is quadratic, this object becomes a Frobenius object. And because it's a Frobenius object, it determines a topological field theory, which should correspond to the string topology operations in the loop space of Vg. But this is something I don't fully understand at the moment, but presumably the structure of this category of Vg in the quadratic case, sorry, in this category of modules in the quadratic case is related to the string topology operations on the loop space of Vg. And this is all I wanted to say. Thank you very much.